For as long as I can remember, the big rule in tech has always been make it smaller. We've gone from computers that filled entire rooms to ones we carry in our pockets. But what happens when you take that idea to its absolute, logical, most extreme conclusion? What if you could build a machine literally one atom at a time?
Really think about that for a second. Switches are everywhere. They're the fundamental building block of, well, everything digital. So what's the ultimate limit? What's the smallest a switch could ever possibly be?
Well, it turns out the answer is this small. Scientists have actually done it. They built a working switch using just a single molecule and one single atom of iron. We are officially playing in the atomic sandbox, and the things we can build now are just mind-blowing. But to really get why a switch this tiny is such a huge deal, we've got to talk about the problem it's designed to solve. And that means we have to dive into the incredibly weird and powerful world of quantum computing. Okay, so the bits in your laptop are like light switches, right? They're either on or they're off. Super simple, super stable. But a quantum bit, a qubit, is a whole different beast. It's more like a spinning coin. It can be heads, tails, or kind of both at the same time. This weird state is what gives quantum computers their power, but it also makes them incredibly delicate and fragile. You need a way to reach in and control one single spinning coin without bumping all the others around it. And that's really the heart of the problem. If we're ever going to build a full-scale quantum computer, we need a totally new kind of switch, one that's small enough to sit right next to a single qubit and precise enough to flip its state without causing a chain reaction. That is the exact mountain this research set out to climb.
So how in the world do you build something atom by atom? You can't exactly pull out a tiny screwdriver and a pair of pliers. No, you need an atomic scale toolkit. And it all starts with 3 key ingredients.
So here's our cast of characters. First, you need a perfectly clean and stable workbench. For that, they use a thin film of magnesium oxide. Then you have the stars of the show, a single atom of iron, which is going to act like our anchor, and this cool-looking molecule called iron phenylcyosinine. We're just going to call it FEPC, because that's way easier to say. This molecule is the real heart of our switch.
Now, the way they put this thing together is just incredible. They use a device called a scanning tunneling microscope, or STM, which basically acts like a pair of atomic tweezers. Its super sharp tip can literally go in, pick up one single FEPC molecule, drag it across the surface with insane precision, and then drop it right on top of that lone iron atom. When it sticks, you get this new complex, and that is our switch.
All right, so we've built it. It's there. But what does it actually do? Well, any switch worth its salt needs at least 2 different states, right? An on and an off. And when you're working at this scale, one of the best ways to create those states is by using magnetism. And it turns out this tiny machine has 2 distinct personalities it can switch between. The researchers call them state A and state B. Under the microscope, one literally looks brighter than the other. But here's the crucial part. In state A, the whole complex is magnetic, so let's call that our on state. Then, in state B, the magnetic fields inside the molecule kind of cancel each other out, making it non-magnetic, and that's our off state. Just like that, we have a magnetic on-off switch.
Okay, that's awesome. We have an on and we have an off, but how do you actually flip it? How do you control it? This is where the design gets really, really elegant. You don't need some big, clunky lever. All it takes is a tiny little zap.
The secret sauce is a property called bistability. It's a fancy word that just means the switch is happy to stay in either the on state or the off state. It won't just flip by itself. To make it change, the scientists just park the tip of that same microscope right over it and send down a tiny pulse of electricity. And that little jolt is all it takes to reliably toggle it back and forth.
But you might be wondering, why does this work so well? Well, it all comes down to that single iron atom we put there at the beginning. If you just had the molecule by itself, the energy you'd need to flip it is pretty high, 187 millielectron volts. It's basically stuck in place. But look what happens when you add that one iron atom. The energy barrier just plummets down to 51. It suddenly becomes easy to flip. That single atom is the key that unlocks the whole thing. So we have a switch, we can turn it on, we can turn it off. That is awesome. But remember the whole point. The goal was to control other things. Can this tiny machine actually do its job? It's time to put it to the ultimate test. The experiment they designed is so clever. They built one of their switches, and then right next to it, they placed another separate molecule to act as a target. The big question is, if we flip our switch, Does the neighbor even notice? Can its little magnetic field reach out and have an effect? And here it is, the big aha moment. They used a special technique to listen in on the target molecule's magnetic signal. With the switch turned off, the target was humming along at 12.749 gigahertz. Then, they flipped the switch on, and look, the target's frequency clearly and immediately jumps up to 12.802 gigahertz. It absolutely worked. The switch is talking to its neighbor. That difference right there, that clean 53 megahertz shift, that's the smoking gun. It is undeniable proof. This isn't just some cool lab curiosity anymore. This is a functional atomic-scale device that can predictably control the quantum state of something else. In other words, we have control. And this wasn't a one-time fluke. They did it again and again. They'd turn the switch on, and the target signal would jump high. They'd turn the switch off, and the signal would drop back low. On, off, on, off. It responded perfectly every single time. This is reliable, reversible control. Exactly what you need to build any kind of computer. Okay, let's zoom out from the atomic world for a second and just think about the big picture here. We've seen how it's built. We've seen how it works. But why is this one single solitary switch such a massive leap forward? You know, I think the researchers who did the work put it best. This isn't just about one switch. It's a proof of concept. It's a blueprint. It shows that we can use the ideas from molecular machines, building complex things from the bottom up, one piece at a time, to create the hardware we need for real, scalable quantum computers. So, what's the bottom line? Let's break it down. Scientists use a single molecule to build a magnetic switch. They can control it with a tiny zap of electricity. And they proved, for the first time, that it can control the magnetic state of its neighbor. This thing is a brand new, fundamental building block. It's the bridge that connects the world of chemistry with the world of quantum computing. And that's really the question this leaves us with, isn't it? We've now shown we can build these tiny machines and use them to poke and prod the quantum world with incredible precision. So if this is the new atomic-sized Lego brick, what kind of incredible things are we going to build next? The possibilities are just staggering to think about. Thanks for tuning in.